Hello everyone, Assalamu alaikum. This is the Resit revision for the module Signal Processing and Circuits for the academic year 25-26. In this revision, we'll be covering examples of problems that are similar to the difficulty and skill set needed for your Resit exam. So without further ado, just to keep this brief, I will be solving these problems one by one with steps. So let's start with the first problem. Number one, a periodic sawtooth waveform, y of t, varies linearly from minus 2 volts to positive 2 volts over each period of t equals 4 seconds. So the question is, state whether this waveform is energy signal or a power signal or neither, and justify your answer with the appropriate definitions and calculations. So what we have to first thing to do here is visualize the signal to identify what type of signal it makes. So we said it linearly varies from minus 2 to positive 2, which means if I'm to plot it, let's say this is my y of t, and this is my time, it goes from minus 2 to positive 2 over a period of 4 seconds. So if I take these 4 seconds to be from negative 2 seconds to positive 2 seconds, it means that negative 2, it goes from minus 2 to positive 2. So this is the shape of my sawtooth signal. And then it repeats this shape. It goes again from minus 2 to positive 2, and from minus 2 to positive 2. So this is the sawtooth signal we're looking for. It's a periodic signal. Now if you look at this signal, the signal is periodic, but it has finite number of discontinuities, and the area under it is finite, even though it's periodic. So therefore, the signal is, so y of t is periodic. And y of t has finite number of discontinuities, which means that this is number of discontinuities. Let me just rewrite this. So this way, this is a power discontinuities. Yes. So therefore, y of t is a power signal. So this answers the first part of the question, to state whether this is an energy or power signal. Then we have to justify our answers with appropriate definition and calculation. So here we gave the definition of a power signal. Next thing, all we have to do is just calculate. And if we're able to calculate the finite power of the signal, then we complete the answer. So for that, we'll use the equation for power, which is the power of a signal is equal to the limit of 1 over t, the integral over 1 period, which is minus t over 2, to t over 2 of f of t squared with respect to time, dt. So if I substitute this here, we already have this equation. So if you look at the graph, you can see that y of t is actually equal to t, because when t was negative 2, y of t was negative 2. When t was 0, y of t was 0. When t is 2, y of t is 2. So y of t is equal to 2, to t, sorry. And then we have the period t is equal to 4. So I already have that from the question. So just by substitution in this formula over here, what I will get is that the power of the signal is equal to the limit of 1 over 4, given that my period t is 4, the integral for minus 4 over 2 to 4 over 2 of f of t, which is t squared with respect to time, which is equal to 1 over 4 the integral from -2 to 2 of t squared with respect to t. Now the integral of t power 2 is t power 3 over 3, so it equals to 1 over 4 t cubed over 3 with integration limits from -2 to 2, which is equal to 1 over 4 times 3, and then we'll substitute the upper limit, which is 2 cubed minus -2 cubed, which is equal to 8 plus 8 over 12. So this is equal to 16 over 12, which is equal to 4 over 3, and the unit of power is watts. So this is the answer for question 1. All you have to do is just evaluate the power using the power formula and then substituting the value of your function f of t, which in our case is y of t. So now let's move on to question number 2. A source provides the voltage Vs of t, which is equal to, so this Vs is equal to 50 cosine 90 t to a series RLC circuit as depicted below. Now, given that the value of R is 200 ohms, so let's write it down here, 200 ohms. The value of L is 20 Henry, and the value of C is 250 microfarads. Can we evaluate the following? So let's start with the first part. Can we calculate the total impedance? So the total impedance phasor, which means we need it in the form of a magnitude and an angle. So as usual, this is easy and simple that these are connected in series, therefore their total impedance is equal to the addition of each individual impedance, ZR plus ZC plus, or sorry, let's keep the order, ZR plus ZL plus ZC. So keeping that in mind, let's evaluate each and every impedance. ZR is given. ZR is equal to 200. So let's just call this formula star. ZR is equal to 200 ohms. And then let's evaluate ZL and ZC. So ZL is equal to J omega L. We already know L is 20 Henry. Where do I get omega? We'll get it from here because it's always in the formula of V peak cosine omega t plus theta. So omega is equal to 90, which means this is J 90 times 20, which is equal to J 1800 ohm. And then we'll find ZC, and we know that the impedance of the capacitor ZC is equal to 1 over J omega C, which is equal to minus J 1 over omega C. Omega is the same 90, so minus J over 90 times the capacitance C, which is 250 micro, and micro here is 10 power minus 10. Minus 6. So this is the capacitance impedance, which is equal to minus J 44.44 ohms. So now that we have ZR, ZL, and ZC, we can substitute them in star. So we can say that then the total impedance Z is equal to 200 plus J 1800 minus J 44.44, which is equal to 200 plus J 1755.55. So this is the impedance, but it's not the phasor. We just got it in a rectangular form. So what you have to do now is convert from rectangular form to polar form. So you can say that the magnitude of Z is equal to the square root of the real part squared plus the imaginary part squared. which is equal to 1766.9. And we can say that the angle of Z is equal to tan inverse the imaginary part, which is 1755.55, divided by the real part, which is equal to 83.5 degrees. And based on that, the final answer, which is the phasor of the impedance, the one that we're asked to find here, is equal to 1766.9 e power j the theta, which is 83.5 degrees. So this here is final answer. So this is the impedance seen at the voltage source, which is the total series impedance. I think we refer to it as Z, so I'll remove the T. Now let's look at the second part of the question. Using the phasor method, determine the steady state of the current in the circuit. So if I go back to the circuit, you'll notice that it is connected in series, which means that the current I is the same for all of them. And we can apply Ohm's law, which states that the current I must be equal to the voltage divided by the impedance. Now I already have the voltage from the question. We're given that Vs is equal to 50 cosine 90. So it's easier to use the phasors and then revert back to the time frame. So I'm going to say phasor I, phasor V, phasor Z. We know that V of t is equal to 50 cosine 90 t, which means that the phasor of V will be equal to 50 e power j 0, or in other words, 50. And we already evaluated the phasor of the impedance Z from part 1 in the question, so we can say that Z phasor is equal to 1766.9 e power j 83.5. And then just substitute it, so we can say that the phasor of the current is equal to 50 divided by 1766.9 times e power j 83.5, which means that the current is equal to 0.028 e power minus j 83.5. Now this here is the phasor, but we're asked to find the I of t, which means we have to rewrite it as a cosine term. Therefore, we can say that I of t is equal to 0.028 cosine. Omega is the same because the circuit is linear, so 90t minus 83.5, which is the phase angle of the current in amperes. And this is the answer for the second question. So now let's move on to the third part of question 2, which is derive the frequency response function h of j omega, which is defined as VL over Vs. So the output is the voltage across the inductor L. So we can say that we can use voltage divider rule. So using voltage, let's say use voltage divider rule. Let me just fix this. So the voltage divider rule states that if your output is the voltage across an element divided by the total voltage, and all of your elements are connected in series, then your transfer function would be equal, given that it's equal to VL over V total, will be also equal to the impedance of that element, ZL over Z total. And we have already evaluated ZL from the first part of the question, which was J omega L, which was J 1800. So we have it from here. This is ZL. So I'm just going to write it down, which is J 1800 divided by the total impedance, which I also have as from the first part here, this part over here, 200, 1 plus J 1755.55. So this is the transfer or the frequency response function, and we can of course enhance further on it if you want to apply or evaluate the complex algebra division. And then we're asked to find the gain and the phase shift of this circuit. So to do so, I'll have to actually evaluate the magnitude. So the gain is actually the magnitude of h of j omega, and the phase shift is actually the theta or the angle of h of j omega. So the magnitude of h of j omega would be equal to the magnitude of, let's rewrite it just real quick. So this is j omega, which is j 1800, and here we have 200 plus j 1755.55. So the magnitude will be the magnitude here divided by the magnitude here, which we can evaluate, which is equal to 1800 divided by the square root of 200 squared plus 1755.55 squared, which can be easily evaluated as 1.018. So this is the magnitude of this circuit, of the gain of the transfer function of the circuit. Phase shift could be the angle of J 1800 minus the angle of the second denominator term, which is 200 plus J 100, 1070, 755.50. Now we already have evaluated the angle of the total impedance from part A, which was 83. The angle here, because the number is purely imaginary, would be equal to 90 degrees minus this angle, which we already evaluated previously to be 83.5. So we already evaluated it here in this bit. So we can say 83.5, and therefore the phase shift will be 6.5 degrees. So that would be the answer that we're looking for, the magnitude and the phase shift. Now let's move on to the third question. So in the third question, we're asked to consider this Laplace domain transfer function, v2 over v1, which is equal to s plus 5 divided by s squared plus 16s plus 60. And you're requested to, 1, express the transfer function in the normalized form. So in the normalized form, the first step would be to try to first factorize the denominator. So we have s plus 5 here divided by, now we're trying to factorize this by finding any numbers that if multiplied will give me 16, if added will give me 16, and these will be 6 and 10. So that would be step 1, to factorize. Step 2, we want to rewrite it in a form that s would be added to a number, that is 1. So instead of s plus 5, I want to be s multiplied by a factor plus 1. So what I would do is I'll take 5 out as a common factor. Here I'll have s over 5 plus 1. And then I'll do the same at the denominator, so it will be 6 times s over 6 plus 1 times 10 times s over 10 plus 1. And then I'll simplify, so divided by 5 is 1, divided by 5 is 2. And then my normalized form will be h of s is equal to S divided by 5 plus 1 divided by 12, because 6 times 2 is 12. 12 S over 6 plus 1 times S over 10 plus 1. So this is the normalized, sorry, this is the normalized form that we are requested to express. Moving on to the second part of the question, can we derive the terms of omega for the gain h of j omega? Derive in terms of omega, which means we don't have the value of omega, so our answer will have omega in it as an unknown value. And what we have, we need to find the gain in decibels and the phase in degrees. So we can say that the first thing is, from part 1 I have h of s, so from part 2 I'll need h of j omega. So I'll just rewrite h of s as h of j omega, which will be j omega over 5 plus 1 divided by 12 times j omega over 6 plus 1 times j omega over 10 plus 1. That will be step 1, to rewrite h of s as h of j omega by replacing every s by j omega. Step 2, we want to find the gain in decibels. So step 1, let's find the gain. The gain is equal to the magnitude of h of j omega, which is equal to, I want to find the magnitude. Let me just create some space. So if this is h of j omega over 5 plus 1, 12 j omega over 6 plus 1, j omega over 10 plus 1. So this magnitude will be the magnitude of the numerator divided by the magnitude of the denominator, which is equal to, now I'll just use complex algebra, the magnitudes are equal to the square root of omega over 5 squared plus 1 squared divided by magnitude 12 is 12. Here we have omega over 6 squared plus 1 squared times square root of omega over 10 squared plus 1 squared. So that is the gain. But the question was not just find the gain, it says find the gain in decibels. So we know that gain in decibels is equal to 20 log the gain. So I will apply this, and then I'll have gain in decibels, and apply laws of logarithms will give me 20 log square root omega over 5 squared plus 1 squared minus the ones in the denominator will be negative 20 log 12 minus 20 log square root omega over 6 squared plus 1 squared minus 20 log omega over 10 squared plus 1 squared square root. So now that we have this, it's 10. This is the gain in decibels that we are tasked to find. The next part would be to find the phase in degrees. And similarly, the phase will be the phase of this part. So let's just copy it here. So the phase would be the phase of this bit will be the phase of this bit, which is equal to the phase of numerator, the angle of j omega, the angle of this complex number, minus the angle of the number 12 minus the angle of the complex number j omega over 6 plus 1 minus the angle of j omega over 10 plus 1. Now if I'm to evaluate these angles, we'll see that it's equal to tan inverse the imaginary over real, which is omega over 5, minus, this is going to be 0 because it's a positive real number, minus the angle of, minus tan inverse. So I'm just using complex algebra rules here, omega over 6 minus tan inverse omega over 10. So this is the angle of h of j omega. And that is the angle in degrees, which is the second part of the question. And if you notice, we have omega here because we don't know the value of omega, we cannot substitute to get an exact value. And that's why we gave it in terms of omega. Moving on to the third part of the question, which states sketch the bode plot for gain, clearly indicating any features. So if I want to plot the gain, I'll go back to the normalized form that I had here and then derive from it. So I'm gonna look, this is my transfer function. And if I look here, I know that I have, remember step 1 in the bode plot is to do the normalized form. Step 2 is to identify elements which are constants, poles, and zeros. So I have a constant at equals 12, a constant with the value of 12. Then I have a 0 at 5. Then I have a pole at 6, and then I have a second pole at 10. So we have a second pole at 10. And then I can go ahead and plot the bode plot for gain. So this is my frequency, and this is my gain in decibels, and this is 20, 40, 20, 40 decibels, and then I can start here with 10 power 0, 10 power 1, 10 power 2. We're just doing an approximation. We don't have to be exactly accurate with the scales. And then I can plot each and every element independently. So a constant at 12, it means I'm looking at 20 log 12, which is equal to, let's just evaluate it for a second. It would be a negative value. Okay, it's 21 point something, so it will be approximately here. At 21.5. So it will be a steady line here, representing, sorry, that one is a little tilted, a horizontal line exactly equal to 20 log 12. And then we have the 0 at 5, so I'm going to find 5, which is approximately here, let's say. And the 0 at 5 means that prior to the 0 we are flat. Once we reach the break frequency, it will start to increase with a rate of change of 20 decibels per decade. And then for the pole at 6, say 6 will be somewhere here. It's going to be 0 or flat prior to that. And then once we reach the break frequency of the pole, it will start to drop with a rate of change of 20 decibels per decade. And finally, we have the second pole at 10. This is 10. It will be the same, 0 prior, and then when we reach the break frequency, drops with a rate of change of 20 decibels per decade. And then the final step would be to combine all the effects. So we'll start with the 20, and then once we reach, let's just define our points of change. So here we have 3 points of change per se at 5, and then at 6, and then at 10. We'll just keep these lines as a reference. So until we reach 5, we only follow the gain of the constant. And then between 5 and 6, we have only the 0, which is increasing. And then between 6 and 10, we have the positive 20 decibels and the negative 20 decibels countering each other out, which means that it will be stationary or flat. And then at 10, we'll have positive 20 and negative 40, which means we will drop. Now let's evaluate, let's write down the rates of change here. So here we have 0 decibel per decade change, it's not changing. Here we have positive 20 decibels per decade. Here we have 0 decibels per decade again. And here we have negative 20 decibel per decade. So the gray line represents the overall Bode plot gain for the circuit. Now, if you notice here, it says key features such as corner frequencies. So these are the 5, 6, and 10. The slopes, which are the decibels per decade, and asymptotic behavior. So the overall behavior. So that means you have to clearly indicate these in the figure. It doesn't have to have an accurate scale, but it needs to have clear indications of break frequencies and rates of changes. The final part of this question is if the input is an impulse function. So if V1, we go back to the question, we here, if V1 here was a pulse, what will be the value of V2? So just reminder, h of, let me change in color. If the input was if the function was h of s was equal to V2 of s over V1 of s, then V2 of s is equal to h of s multiplied by V1 of s. And it says here, find me V2 of t if you know V1 of t. So what I'm going to do with that information is, I'm going to say if V1 of t is equal to delta t, then V1 of s is equal to the inverse transform here, which is equal to 1. And you can find that from the Laplace transform tables, which will be available in your formula sheet during the exam. So based on that, if V1 of s is 1, then V2 of s is actually equal to h of s from here. And I already have h of s in the question. Let me just take it, which is this value. Let's put it here. Let's just take it as this and just copy it here for reference. So it's equal to s plus 5 divided by, we already factorized this in part 1, s plus 6 times s plus 10. Now I can take this bit out. Okay. So what we'll do is we will use partial fractions because we want to find v2 of t. So we need to find the inverse transform. But in order to do that, we need to simplify it into something that we can find on the table. So what I will do is use partial fractions. So if I'm to use partial fractions, we can say that v2 of s is equal to s plus 5 over s plus 6 times s plus 10, which is equal to a over s plus 6 plus b over s plus 10. And all you have to do now is solve for a and b, which is straightforward if you want to find a. So to find a, we multiply by the denominator of a, which is s plus 6, and let s equals negative 6. So what do I get from that? We do that, what you get is you'll multiply here by s plus 6, s plus 6, s plus 6. These will cancel each other out. These will cancel each other out. And if you let s equals negative 6, then this part will be equal to 0. And here you'll have minus, so we'll substitute in place of every s by negative 6. Minus 6 plus 5 divided by minus 6 plus 10 is equal to a, which means that a is equal to 1 over 4. Similarly, if I want to find b, then I'll multiply by b's denominator, which is s plus 10, and just do that. So we'll multiply by s plus 10 and let s equals minus 10. So let me just write down the step. To find b, multiply by s plus 10 and substitute s equals negative 10. So what will that give me? These two will cancel each other out. These two will cancel each other out. If s is minus 10, this means this is 0. And that gives me that the left-hand side of the equation with s equals 10 will be minus 10 plus 5 over minus 10 plus 6. And on the right-hand side of the equation, I'll only have b, which means that b is equal to minus 10 plus 5 is minus 5, minus 10 plus 6 is minus 4. So 5 over 4. So these are the values of a and b. Now I can substitute a and b, so I can say that, well, therefore, v2 of s is equal to a, which is 1 over 4 over s plus 6 plus b, which is 5 over 4 over s plus 10. And we can introduce the inverse transform to find the v of t, v2 of t, and from the tables, you can find the tables will be available in your formula sheet. You can find that v2 of t will be equal to 1 over 4 e power minus 6 t plus 5 over 4 e power minus 10 t. And this would be v2 of t that you're tasked to find. So this kind of concludes the last part of question 3. Now let's move on to question number 4. So here, what do we have to do? Here we have to consider this parabolic function depicted in this figure below. And it's defined as x of t is a times, let me remember. I think this was the correct representation, a of t over t squared We can actually lose the brackets. I think I'm over adding them here. For t equals from minus t to t. So let's evaluate that. So let's evaluate that. We are given the x of t value and we are trying to find the Fourier series coefficients a of 0, a of n, and b of n, which represents the signal in its trigonometric form. So now, if you look here at a of 0, a of n, b of n, let's first start looking at the function. If you look at the function, you'll notice that it is mirrored about the vertical axis. So whatever is happening here is here. Or in other words, x of t is equal to x of negative t, which means that x of t is even. And if the function is even, we can directly say that b of n will be equal to 0 without any evaluation. So that means all I have to do is find a of 0 and a of n. So to do that, I'll just use the formula to evaluate a of 0. So a of 0 is equal to, let me just copy the formula, 2 over t. By the way, this formula will also be available on your formula sheet. 2 over t over the integral over 1 from 0 to t times x of t dt. Now, if I'm substituting, the period is from negative t to t. Let's assume that the value here is a based on that value. So let's substitute x of t, so 2 over t, the integral from 0 to t. And instead of x of t, I'm going to use the value given in the equation. In the question, a of t over t squared with respect to t. And then let's do the integral. So we can take a outside the integration, and we can take t squared outside the integration. It will be the integral from 0 to t of t squared dt, which is equal to 2a over t cubed times t cubed over 3 with limits from 0 to t. And if you substitute the limits, the upper limit and the lower limit, it will be 2a over t cubed times t cubed over 3 minus 0. These two cancel each other out, and we can say that a0 is equal to 2a over 3. So this is the first coefficient, a0. The next one is a of n, and again, all we have to do is just copy the formula for a of n, which states that a of n is equal to 2 over t, the integral from 0 to t of x of t cosine n omega naught t dt. But we know that omega naught, let's keep that here, is equal to 2 pi over the period. And the period here is 2t because it goes from minus t to t over 2t, which is equal to pi over t. So what I will do is I'll substitute this here in place of omega naught. I'm going to substitute this value over here. And then in place of x of t, I'm going to substitute the value that I'm given in the or the formula that I'm given for x of t over here. So this becomes, I'm going to substitute this one. So this integral then becomes a of m is equal to 2 over t, the integral from 0 to t. Now in place of x of t, I'm going to put its value, which is a t over t squared. Let me double check. Yes, a t over t squared times cosine n, sorry, n pi. So instead of omega naught, I'm putting pi over t capital with respect to time. And then what I would do next is I'm going to use the formula of integration by parts. So this is what you want to do. Use the integration by parts, which is the rule that says that, so I'm just going to write the rule here. The integral of u dv is equal to u times v minus the integral of v du. And you'll have to do that twice because the power here is 2. So you'll have to integrate by parts over 2 steps. I'm not going to delve into the integral. You can practice it, and there is many examples of us using it in the Fourier series tutorial and lecture. So you can go back to that. So a of n will be equal to, once you do the steps of the integration by parts, it will be equal to 4a minus 1 power n over n squared pi squared. So this would be a of, and now in the exam I expect you to do the steps. So here we have a of 0, a of n, and b of n. Now to put it in trigonometric form, we'll have to go back again also to the formula to evaluate it. So if you are to put your Fourier series in trigonometric form, all you have to do is just substitute in the formula of the trigonometric form, which is available as well, your x of t expressed as a Fourier series will be equal to a0, which is a0 over 2, so it will be a over 3 plus the trigonometric term, and because we don't have the sine term, because b of n is 0, we'll only use the cosine term. So it will be 4a over pi squared, and then the term with n on it, which is negative 1 power n over n squared for n equals 1 to infinity. So that is a of n times cosine n omega naught t, which is n pi over t. So this is the trigonometric form of the Fourier series after evaluating